In this video, we will see the third case of viscous flow, which is flow of viscous fluid between two parallel plates having relative motion. Here also for this case, we are having two parallel plates which are d apart, as we saw that for the second case of viscous flow between two parallel plates. Only the difference is that this upper plate is moving with a constant velocity u. तो कुछ चीज़ें हैं जो सेम रहेगी सेकंड केस के जैसे, सो वो मैं वापस से नहीं डिराइव करने वाली हूँ. लाइक द फोर्सेस एक्टिंग ऑन द फ्लूइड, that will remain the same. This equation we had got del p by del x is equal to del tau by del y. Then we took Newton's law of viscosity और tau is equal to mu du by dy हमने लिया था, जिससे वेलोसिटी डिस्ट्रीब्यूशन u का इक्वेशन मिला था. u इज इक्वल टू 1/mu del p by del x y square by 2 plus c1y plus c2. यहाँ तक का जो है वो सेम था. अभी हम लोग स्टार्ट करेंगे फॉर दिस केस. नाउ इट डिफर्स. एंड वाई इट विल डिफर? बिकॉज अपर प्लेट इज मूविंग विद अ कॉन्स्टेंट वेलोसिटी ऑफ u. तो y इक्वल टू ज़ीरो है तब u इक्वल टू तो ज़ीरो ही है, पर जब y इक्वल टू d है तब u इक्वल टू u हो जाएगा. यूजिंग दिस बाउंड्री कंडीशंस, keeping it in the first equation, we'll get the values for c1 and c2. So 0 is equal to 0 plus c1 into 0 plus c2. Therefore we get c2 is equal to 0. And then we'll apply the second boundary condition, which is y is equal to d and u is equal to u. So it will be capital U equal to 1/mu del p by del x into d square by 2 plus c1d plus 0, because c2 is 0. Therefore we'll get c1 is equal to u by d. It's c1d, so d will be divided. Therefore we get u by d is equal to 1/mu del p by del x into d by 2 plus c1. Therefore c1 will be equal to u by d minus 1/2mu del p by del x into d. Then we'll substitute the values of c1 and c2 in the first equation and we'll obtain the equation for velocity. So we get u is equal to 1/mu del p by del x y square by 2 plus u by d minus 1/2mu del p by del x into d whole multiplied by y plus 0, because c2 is 0. Therefore we get u is equal to 1/2mu del p by del x y square plus uy by d minus 1/2mu del p by del x dy. Here we can take this 1/2mu minus del p by del x is common. So it will be 1/2mu minus del p by del x into dy, because this minus minus will become plus, and here it will be minus dy minus y square plus uy by d. So this is the equation for velocity. Here we can see that velocity distribution will depend upon u and del p by del x. And here we'll be having two cases. एक तो जब प्रेशर ग्रेडियंट नहीं है तब, और दूसरा केस जब प्रेशर ग्रेडियंट प्रेजेंट है तब. दैट इज़ व्हेन del p by del x इज़ इक्वल टू 0 एंड व्हेन del p by del x इज़ नॉट इक्वल टू 0. अभी अगर ये 0 रखते हैं तो इक्वेशन में क्या हो जाएगा, u इज़ इक्वल टू यू आई बाई डी बच जाएगा. तो इस केस के लिए हमारी वेलोसिटी डिस्ट्रीब्यूशन कैसी होगी? सो इट विल बी लीनियर like this. Velocity profile will be linear, and this type of flow is known as pure coed flow. It's necessary to remember this, that here when the pressure gradient is 0, then the flow will take place due to shear driven velocity component, and that type of flow is known as pure coed flow. And now when del P by del X is not equal to 0, then for that the velocity profile will be parabolic like this, and this type of flow we call it as coed flow. So again I'll repeat that when there is no pressure gradient, flow will take place due to shear driven velocity component, and that type of flow we call it as pure coed flow. When pressure gradient is present, then the velocity profile will be parabolic and that flow is coed flow. Next, we'll see the shear stress distribution. For that, we'll be using the Newton's law of viscosity. Tau is equal to mu del u by del y. We already have derived the equation for velocity. We'll just use that. Mu del by del y, uy by d plus 1 upon 2 mu minus del p by del x into dy minus y square. This del by del y, that is differentiation with respect to y. So mu into u by d, because uy by d differentiation of y is 1, then 1 upon 2 minus del p by del x into differentiation of y is 1 and y square, it will be 2y. So this will be mu u by d plus 1 upon 2 minus del p by del x d minus 2y, or we can write it as d by 2 minus y, just multiplied 1 by 2 in the bracket. Now we are having this boundary conditions. When y will be 0, then tau will be equal to tau 1, and when y is equal to d, tau is equal to tau 2. So tau 1 will be equal to mu u by d minus del p by del x into d by 2, and tau 2 will be equal to mu u by d plus minus del p by del x d by 2 minus d. d by 2 minus d, that is d minus 2d by 2, which is minus d by 2. And what will be the shear stress at center of the plate? Then at center of the plate, y is equal to d by 2. Therefore, we'll place that in the equation of tau, and we get tau is equal to mu u by d, because the second term will become 0, minus del p by del x into d by 2 minus d by 2. So this will become 0. Therefore, we get tau is equal to mu u by d. अभी हमें कैलकुलेट करना है वो डिस्टेंस जब shear stress हो जाता है 0. तो we'll place tau is equal to 0 and we'll find y. Therefore we get 0 is equal to mu u by d plus minus del p by del x into d by 2 minus y minus mu u by d is equal to minus del p by del x into d by 2 minus y. Then on further solving this, we are taking this del p by del x in the denominator. It will be minus will get cancelled, and mu u by d del p by del x is equal to d by 2 minus y. Therefore we get y is equal to d by 2 minus mu u by d into 1 upon del p by del x. This is our shear stress distribution diagram. Here tau 1, this represents tau 1, this represents my tau 2. At d by 2, tau will be equal to mu u by d. That is here somewhere I'm representing that this is my d by 2, and my shear stress will be equal to mu u by d as we have derived it. And we have also found the distance at which the shear stress is 0. This is my shear stress distribution diagram. With this, we have understood all the three cases of the viscous flow. Next, we'll be solving some examples. Don't forget to subscribe my channel. Thank you.